The U.S. just cracked Iran's nuclear fortress. A 30,000-pound B-2 strike collapsed the mountain, burying their ambitions forever.
January 16th, 2026, 0200 hours. The Zagros Mountains do not sleep. They wait. Here in the calm governorate of Iran, the geology is not merely a landscape. It is a weapon. The air is thin, biting cold, and silent. There is no sound of machinery, no hum of industry, only the wind whistling through the jagged peaks of the Zagros Folded Zone. To a satellite passing overhead, this is nothing but a barren ridge of sedimentary rock. But this is a lie. Beneath 80 meters of marine carbonates, limestone, and dolomite, the earth is hollow. Buried inside the mountain is the Fordow Fuel Enrichment Plant. It is the apex of what military strategists call a hard and deeply buried target, or HDBT. This is not a bunker built of poured concrete. This is a facility excavated into the crust of the planet itself. The silence on the surface is deceptive. Down in the darkness, centrifuges are spinning at supersonic speeds. The stakes here are not measured in territory, but in time. If the centrifuges inside Fordow continue to spin, the timeline to a nuclear breakout shrinks from months to weeks. But the problem for the United States Air Force is the shield. The primary defense of Fordow is not a surface-to-air missile battery. It is not a jamming tower. It is the mountain. Specifically, it is the Qom Formation. This is a thick sequence of rock formed millions of years ago at the bottom of an ancient ocean. It is composed of limestone and dolomite. To the uninitiated, this is just stone. To a kinetic engineer, it is a nightmare. Dolomite in this region has a compressive strength ranging from 80 to 140 megapascals. That is roughly 11,000 to 20,000 psi. Compare that to the reinforced concrete used in standard bunkers, which typically fails at 5,000 psi. The mountain is 4 times stronger than the hardest man-made fortification, and there is 80 meters of it. This overburden acts as a geological shield. It is a chaotic, layered armor of variable density, full of fracture zones and dipping bedding planes that can deflect a penetrating weapon, turning it sideways before it ever reaches the target. This phenomenon is called J-hooking. If a bomb J-hooks, it fails. It explodes harmlessly in the rock, hundreds of feet above the objective. But the physics of war are about to change. High above the troposphere, at an altitude of 50,000 feet, something is moving. It does not exist on radar. To the electromagnetic spectrum, it is a glitch. To the atmosphere, it is a shadow. This is the Northrop Grumman B-2 Spirit. It is a flying wing, a seamless integration of composite materials and mathematical geometry designed to cheat the laws of detection. But tonight, its most terrifying quality is not its invisibility to radar. It is its silence. Conventional jets scream. Their afterburners tear the sky apart. But the B-2 is different. Its 4 General Electric F-118 turbofan engines are buried deep inside the wing structure. The air intakes are scalloped to hide the compressor blades. The exhaust is routed through serpentine ducts lined with heat-absorbing tiles, then ejected over a cooling trench on the trailing edge. This process, known as shear layer mixing, diffuses the hot jet wash with cold ambient air before it leaves the aircraft. It kills the low-frequency rumble. From the ground, 50,000 feet below, the B-2 is acoustically invisible. If you were standing on the peak of the mountain, you would hear nothing. Maybe, just maybe, a faint sound like tearing paper or a rushing wind, but only after the aircraft had already passed. By the time you hear the wind, the payload is already falling. And the payload is heavy. Inside the belly of the bomber, the weapon bay doors are held shut against the slipstream. Suspended on the rotary launcher assembly is the largest conventional guided weapon in the American arsenal, the GBU 57A/B the MOP, Massive Ordnance Penetrator. This is not a bomb. It is a 20.5-foot-long dart made of Eglin steel. It weighs 30,000 pounds. That is 13.6 metric tons of high-strength alloy, specifically formulated to survive an impact that would liquefy normal steel. Eglin steel, or EES1, is a marvel of metallurgy. It contains nickel, silicon, chromium, and tungsten. It has a yield strength of 245,000 psi. It is designed to remain rigid while punching through solid granite at supersonic speeds. Most bombs rely on the explosion to do the work. The MOP relies on kinetic energy. The explosion is just the afterthought. The weapon is a physics equation wrapped in steel. The formula is simple. Kinetic energy equals 1/2 mass times the velocity squared. To maximize this energy, the B-2 must release the weapon from the stratosphere. Gravity does the rest. As the 30,000-pound steel rod falls, it accelerates. In the thin air of the upper atmosphere, drag is negligible. it builds speed. By the time it hits the denser air of the lower troposphere, it is traveling at Mach 1.3. That is 440 meters per second. When you combine a mass of 13,000 kilograms with a velocity of 440 meters per second, you generate roughly 1.32 gigajoules of energy. Let me put that into perspective. That is equivalent to a 2,000-ton freight train hitting a solid wall at 80 kilometers per hour. And all of that energy is concentrated into a frontal area of just 31 inches. But here is the problem. Even with 1.3 gigajoules of energy, the math says it is not enough. The geologists and physicists at the Pentagon have run the simulations. They know the S number, the penetrability index of the Zagros limestone. A single MOP striking this mountain will penetrate approximately 15 meters into the rock before stopping. 15 meters. The target is 80 meters down. If the bomb detonates at 15 meters, it creates a camouflage. This is a contained explosion. The rock absorbs the energy. The gas bubble expands, crushing the stone into powder, but the shockwave attenuates before it reaches the centrifuge hall. The lights in the facility might flicker, dust might fall from the ceiling, but the centrifuges will keep spinning. Accelerometer data confirms terminal depth. Layer count 0. Initiate. To defeat the mountain, the United States Air Force must employ a tactic known as the double tap, or, in the grim humor of the pilots, mowing the lawn. This is not about brute force. It is about precision so extreme it borders on the impossible. The plan requires dropping two 30,000-pound weapons in sequence. They must hit the exact same GPS coordinate. The first bomb is the excavator. It hits the mountain at Mach 1.3. It smashes through the first 15 meters of rock and detonates. It does not destroy the facility. It destroys the overburden. It blasts a crater, fracturing the limestone, turning solid rock into rubble and dust. Then, seconds later, the second bomb arrives. It must navigate through the dust plume of the first explosion. It must dive into the crater created by its brother. It travels through the empty air and loose debris of the first hole, retaining its kinetic energy. It strikes the undisturbed rock at the bottom of the crater, 15 meters below the original surface. It starts its penetration where the first one died. It drives another 15 meters deeper. This is the theory of sequential excavation. You do not crack the nut with one hammer blow. You drill through it. But this theory relies on the guidance system working perfectly. The MOP uses grid fins, lattice-shaped control surfaces that fold out from the tail. These fins provide extreme maneuverability at supersonic speeds, allowing the bomb to adjust its trajectory in real time to ensure it threads the needle. If the second bomb drifts just 3 meters to the left, it hits fresh rock. It stops at 15 meters. The mission fails. It must hit the hole. Back in the cockpit of the Spirit, the pilot watches the monitors. The release point is approaching. The bay doors are about to open. The hydraulic actuators are primed to snap the doors wide in less than a second to minimize radar exposure. The pneumatic ejector pistons are pressurized, ready to shove 60,000 pounds of ordnance into the slipstream. The physics of the B-2 are about to be tested. Releasing 27 metric tons of weight instantly shifts the aircraft's center of gravity. The digital flight control system, the GLA, or gust load alleviation, must instantly compensate, adjusting the elevons to keep the plane from pitching up violently. The pilot's finger hovers. The countdown hits 0. Release. The hydraulic actuators scream. In less than a second, the bomb. Bay doors snap open, exposing the internal cavity to the Mach 0.85 slipstream. Instantly, the air inside the bay becomes violent. This is a phenomenon known as Rossiter modes. The high-speed air rushing over the open cavity creates a resonant pressure wave, a thrumming vibration that can tear delicate electronics apart. But the B-2 is ready. Spoiler fingers at the leading edge of the main disrupting the airflow, shattering the resonance into turbulent noise. Then, the shove. Pneumatic ejector pistons kick the GBU 57 away from the aircraft. 60,000 pounds of mass drop free. The bomber shudders, instantly lighter. The flight computer fights the new center of gravity, trimming the elevons to keep the wing level. The doors snap shut. The stealth seal is restored. But below, the physics of freefall have begun. For the first few seconds, the two bombs tumble slightly in the thin air. Then the grid fins deploy. These are not solid wings. They are lattices, like waffle irons made of steel. They bite into the air, stabilizing the 30,000-pound darts. The nose cones tip down. Gravity takes hold. The acceleration is reduced, 100 miles per hour. They cross the sound barrier. There is no boom heard on the ground yet. The weapons are moving faster than their own sound. They are silent executioners falling from the edge of space. The GPS chips inside are locked onto a single coordinate, calculating wind drift, atmospheric density, and trajectory to a tolerance of less than 3 meters. On the ground, the guards at the perimeter fence are shivering in the cold wind. They look up. They see nothing. They hear nothing. Then, the timeline splits. Impact 1. The first MOP strikes the limestone at Mach 1.3. The velocity is so high that the rock does not crack. It flows. The pressure at the tip of the penetrator spikes to 4.5 gigapascals. This is the hydrodynamic limit. For a split second, the solid mountain behaves like a liquid. The Eglin steel casing glows white-hot from friction. It forces its way down, chewing through 5 meters, 10 meters, 15 meters of ancient seabed. Inside the tail of the bomb, the hard target void-sensing fuse, the FMU-159, is waking up. It is not a timer. It is an accelerometer. It feels the intense deceleration of the rock, thousands of Gs crushing against the nose. It is waiting for a drop in pressure, a sign that it has broken through into a tunnel. But it doesn't find a tunnel. It finds only rock. Accelerometer data confirms terminal depth. Layer count 0. Initiate 5,300 pounds of AFX 757 explosive ignite. But this is not an fireball in the open air. This is a camouflage. The explosion is contained by millions of tons of rock. The energy has nowhere to go, so it pushes. The gas bubble expands with terrifying violence. It pulverizes the surrounding limestone into dust. It heaves the rock upward. A crater opens, vomiting a geyser of stone and dust hundreds of feet into the air. The mountain has been breached. The shield is cracked. But the centrifuge hall is still safe, 65 meters below. The lights flicker. The scientists look up confused. They think it is an earthquake. They are wrong. 30 seconds later. The second tap. High above, the second MOP has been watching. It dives into the dust cloud of its brother. The guidance fins twitch, correcting for the turbulence. It must thread the needle. It aims for the center of the fresh crater. It clears the rim. It passes through the 15 meters of empty air and loose rubble created by the first blast. It does not lose energy. It does not slow down. It hits the bottom of the crater at full speed. Now the math changes. The rock here is fractured. It is weakened. The second penetrator drives deep. It passes the 20-meter mark. The 30-meter mark. It buries itself 35 meters into the mountain. The fuse senses the depth. It triggers. Detonation 2. This time, the shockwave is not wasted on the surface. It is deep. It couples directly into the spine of the mountain. A massive compressive wave, a P wave, races downward at 4,000 meters per second. It hits the roof of the centrifuge hall. Here is where the facility dies. The bomb does not need to enter the room. When the compressive shockwave hits the ceiling of the tunnel, the interface between rock and air, it reflects. Physics dictates that a compression wave reflecting off a free surface becomes a tensile wave. Rock is strong in compression. It is weak in tension. The ceiling does not just crack, it explodes downward. Spalling. Massive slabs of reinforced concrete and limestone, weighing tons, are ripped from the roof. They are launched into the facility at the speed of a cannonball. The centrifuges are spinning at supersonic speeds. They are delicate vacuum systems balanced on magnetic bearings. They cannot survive a pebble, let alone a falling roof. The spall slams into the cascades. The aluminum rotors shatter. Shrapnel tears through the vacuum lines. Uranium hexafluoride gas vents into the room, reacting with the moisture in the air to form hydrofluoric acid. The facility is not just crushed, it is chemically poisoned. Back on the surface, the illusion of stability is gone. The mountain heaves. The ground undulates violently via Rayleigh wave propagation. The shockwave reaches the surface soils, and the phenomenon of liquefaction begins. The solid ground turns into quicksand. Ventilation shafts shear off. Intake buildings tilt and sink into the earth. From the crater, a second plume erupts. This one darker, hotter. It is the breath of the mountain, exhaling the pressure of the deep blast. Then silence returns. Seismic stations across the Middle East light up. In Turkey, in Saudi Arabia, the needles dance. The magnitude registers as a 3.5. But the seismologists know this signature. It is too sharp, too sudden. It is not a tectonic shift. It is a cavity collapse. The damage assessment begins immediately. Satellites pick up the thermal bloom of the venting gases. The intelligence analysts look at the data. They don't see a destroyed mountain. The peak is still there. But the facility is dead. The structural integrity of the tunnels has failed. The chimney of rubble created by the second bomb has collapsed downward, burying the sensitive equipment under thousands of tons of rock. To dig it out would take years. To rebuild it would take a decade. This is a mission kill. The cost of the operation? $2 billion for the aircraft, $6 million for the bombs. The cost of the target? Incalculable. A national nuclear program set back by a generation. This simulation proves a brutal truth about modern warfare. We often think of defense in terms of technology, jammers, lasers, interceptors, but the oldest defense is the Earth itself. Geology is the ultimate armor, and yet, kinetic energy acts as the universal breach mechanism. The GBU 57 MOP is not a subtle weapon. It is a brute force application of Newton's laws. It reminds us that there is no sanctuary. If you can find the coordinates, and if you can generate enough kinetic energy, there is no amount of rock that can hide you. The pilots of the B-2 turned for home. They felt nothing of the impact. No vibration in the stick, no sound in the cockpit, just a slight shift in the fuel indicators as they bank away from the Zagros. The war of the future is not just about who has the better microchip. It is about who understands the lithosphere, who can turn the ground beneath the enemy's feet into a weapon. So the question remains, if you were the commander, sitting in the deep bunker, watching the seismic sensors spike, would you feel safe? Or would you look at the ceiling and wonder how thick the rock really is? Fair winds, the physics of war. Never sleep. See you in the next video.